Right. Let's give me a chance to switch this on. And let's start by Werner. Let's start by watching a video. But I haven't got funny videos. It's all boring videos. Well, I'll show you this video. So this is basically, I think this is an ad.
We can watch
that may be so that they've leaked, but they haven't leaked to my computer yet, or ever. I haven't ever seen Game of Thrones. I know it's a TV show, so. Oh, that's excellent, but I'll just pause. So this is a company, Black Ginger. Who know them? No one knows about them. They're a company that does graphics, CGI for movies and ads. Mostly ads, I think. Although I think they were involved with Penguin movies, Happy Feet or Happy Twins, or some Penguin movies. And some of our students work for Black Ginger. And this is one of the ads they did. I think it's behind the scenes stuff. So you'll see as part of the ad. I don't watch television, I don't have a television, so I'm not sure if this is shown on television or movies or whatever. I haven't ever seen it, but it's a nice ad, but this is the behind the scenes. I'm just going to rewind, sorry. I'll interrupt because I want to say stuff. So that's the original shot that they show in the movie, I think. And then this is how they actually shot it. It's on some kind of just airstrip, and then they digitally add all these other elements and change people's clothing. There's no ship. There are no ships. It would have been really spectacular if I'd remembered to actually buy small little lunch bar chocolates and hand it out when I show this video. So that's the kind of stuff that the Black Ginger does. And as I said, we have people who studied with us, who work for them. So, I mean, not all programming that you do eventually is just writing code all the time. Sometimes there's, well, you do write code because everything is code, but it's not all figures and numbers and Java. Sometimes there's sophisticated graphics and modeling involved. I think I've got more of their stuff, but it's not really interesting from a coding point of view. I've got videos like, is computer science only for boys? Is computer science only for geeks? Oh, let's watch that. Because you're not all boys, but you may all be Greeks. Geeks, not Greeks. Oh, sorry, once again, interruption. This is made for some kind of Canadian online school. So if they say anything about Canadian online schools, you know that's why.
I need to know if I'm a geek. Although some people call me geek. If you ask me if I'm a geek, I would ask you, what do you define as a geek?
I'm not a geek.
I would consider myself geek. You're totally geek.
Oh.
Counter-Strike every night.
I'm not a geek.
I don't know how to answer that one.
I think it's cool to be a geek. If I have other cool geeky friends that I can be geeky with.
Computer science is not only for geeks. I don't consider myself a geek.
Computer science is not only for geeks. It's for the kind of person who loves technology and who loves to challenge himself.
It's actually a great program to have fun, you think, use your logic.
Anybody could like computer science.
Not everybody is a geek.
Yeah, we're all geeks. Look at that.
Yeah. Not very funny. And of course, it's entirely inaccurate. Computer science is only for geeks. And listen, we have to, there's a small announcement. We're going to change the schedule a little bit. So I've changed this already so that next Thursday there's a practical test and Friday we have a written test. We have to somehow prepare for this written test because I think all your marks should now be online. Once again, I'm getting to your emails. I didn't get emails that you sent to me. I'll fix the people who are missing. But just check again. We have a small problem because in your previous test, you didn't do fantastically. And I'm sure that I'm to blame for that. I take full responsibility, but now I need your help to help me fix that. So we'll have a two-pronged strategy. Okay? One of the prongs is that I will make this next test a little easier. Obviously, my big mistake was to make the other tests too difficult. But you still have to study for this test. You can't just come and write your name. So we have to talk about what will be in the test. We'll do that next week. Because next week we're not going to talk about recursion. We're going to have a whole test week. So on Monday, I will work through the very first test, which you'll find boring because by now that stuff will seem so easy. And on Wednesday, I'll work through the last test that you wrote. So the one somewhere up above here. So that we are prepared for the next test. I mean, these tests are really interesting. It's not enough to be able to go in front of the computer, because Eclipse is helping you, or the compiler helps you to find your mistakes. But if you really know how to program, and we're not talking about even syntax errors, it's just simply a test, this is working. Many people who can't code well use what is called code and fix. Write a little code, see if it works. If it doesn't work, fix it. And you keep on doing that, just trying different values for for loops, trying different things. That's not the way to program. If you can really think programmatically, you should be able to do it on paper. So these written tests are really important to me, and I can tell a lot from the kind of mistakes that people make. For example, in the previous test, there was 2 questions about just tracing through a program and finding the values for certain variables. And some people did that amazingly well. And then when it came to the last question, which was about arrays, I think, they didn't. Some of those people didn't do very well because they clearly don't know arrays, don't understand the concepts beyond arrays. And vice versa. Some people couldn't trace the program variables and did well on the arrays. So let's have a little easier test. We'll work through the test next week. That means the practical test and the written test won't have much recursion, but it'll have a little bit. Recursion is difficult, so I'm not going to push it. I want to make this test, even the practical test, a little easier. If your grades are too low, university will fire me because they'll say I can't teach. Even though we may think that it's actually your fault for not knowing how to learn, I take full responsibility and I feel that I'm to blame. Okay, I do. I feel really bad. Anyways, so we're going to spend today just talking about recursion, and we'll do this last in yesterday's tab. Were you all at the tab? Okay, that's great. How did it go? Easy. All right. Okay. On the level between easy and difficult, exactly where is all right? Middle, of course. I should have known. Okay, right. So just show your hand. No, everybody please put their hand up. I have invented something fantastic. For thousands of years, teachers have had a problem. Because you ask a question and only a third raise their hands, and then you ask the negation of the question and only the other third raise their hands. And there are a third of people who never raise their hands. But I just thought of the solution. It was so obvious. It was staring us in the face the whole time. What I should do is, I ask everyone to please raise their hands now. All of you, immediately. All of you. I haven't asked the question, raise your hands like this. Everyone has their hands raised. This. Don't worry, I'll try to do circulation. Excellent. Now, lower your hand if you did not finish this exercise. So if you did finish, keep your hand up. Just question 1. Okay, good. Excellent. This is brilliant. Okay, let's just, you can lower your hand. Let's just analyze the situation. Where are you from?
Practical.
Your practical.
Project.
Project. This is what exercise? What? You can.
Oh, yes. I didn't do this on my project.
Oh, project. Family matters. Oh, sure. How's all the projects? Oh, that's excellent. Okay. Well, so the people who did finish it, what does it print? Only one person, yes. Shout. Shout. Powers of 2, yes. You saying? Yes, exactly. 2. Okay. So this prints 2 to the I. But that's not the point. It could have printed something else entirely. It's something worthwhile to do it, because we want to learn about recursion. But I'm still going to quickly do it, even though most of you did it. It can't possibly be fun to watch me program, but I think it's useful just to see what other people do when they program and how they think. That's what I really want to teach you, to think. Well, not to think, how to think. I'm sure you all think already. Okie dokie. Let's just start up Eclipse. Shouldn't have shut it down yesterday. Any interesting videos that I downloaded? This is the most boring videos ever. No, it's about how to do web service programming. You don't want to see it. Actually, that guy is quite funny. We can watch a few minutes if I finish. So if you cooperate, we'll finish quickly and then I'll show a little bit of that video. So let's just, while Eclipse is loading itself, let's just see here what it says. Implement the following recursive function by translating its formula to Java. Oakley dokley, so there's the formula. It takes 2 parameters. We've done that before because we wrote GCD. We did GCD in class. Okay, that's fine. And then there are these conditions. If A is 0, we send back 1. If A is equal to B, we send back 1. If A is more than B, we send back 0. And otherwise, we send back that story. So there's the recursion. But I can do this. I can write an if. I know what I'm going to do. It'll be easy peasy. Okay, fine. And now, and I say, now implement the function. Oh, this looks tricky. MC is the sum where I goes from 0 to C. I can use a for loop, I guess, of KIC. Okay, good. We can do that. Okay, close this. Make a new project. I fixed my clip, so it should work. That 7. Okay, I'll do all of this in that 7. So I'll just make a package. I'll call this package Q1, question 1. And I'll call my Java class Q1 as well. Okie dokie. So they say, write this function, KAB. Okay. Public, static, it's going to send back a value. And it takes 2 parameters. What is it complaining about? This method must return a result. I'm not returning anything yet. And that those conditions were if A is 0, send back 1. If A is 0, send back 1. If A is B, send back 1. Okay, so I can just include it here. If A is 0 or A is equal to B, send back 1. Else, if A is more than B, send back 2. If A is more than B, oh, sorry, not 2, 0. Else, return, and now this lot. I wonder if I can copy paste. Copy, paste. Oh, fantastic. Okay, how long did you tell me? How long did it take?
1 minute.
1 minute.
1 minute, please.
Okay. But you could have done this and still had time to do the project. I'm not blaming you. I'm just saying that if we don't go insane, if we just stay calm, then the stuff isn't really difficult. I've done it millions of times, so it's difficult for me to really judge. I'm sorry. I just want to show you that it's not that terrible, and recursion is really easy if it's given like this. Now we need a function MC, public, static, int, M, parameter is C, and it has to return this whole sum. So I'm going to make a variable sum. I'm going to make I go from 0 up to C. I'm going to say sum equals sum plus, and this term is KIC. Copy, paste, semicolon. Oh, mistake. This method must return. Oh, I forgot the return statement. Return that sum. So I've got one function for K, whose name I chose because of my combinations, which is what this function is really called. And I've got this one other function, M. M is not chosen to mean anything. And I'm going to write a main because, if I remember correctly, they want me to write a table. Complete your program by writing out a table for MC from 0 to 10 for int I, and I can use the same I up to 10, and M of I is equal to M of I. Okay, and that's my whole program. No mistakes? Can I save it? Can I run it? What's your name again? Yes. Arnie. As Arnie said, this turns out the partials too. Why does it turn out the partials too, Harley? You're not exactly sure, but you're kind of sure. Now you must say somebody's name. All the answers in this whole course is just one word. One word answer. Fibonacci is the recursion, but it's not the name I'm looking for. The name I'm looking for is Pascal. Did you do Pascal's triangle at school? Okay. So these KI's, see, I'll point to them and they don't exist. Double click. K, A, B returns the 8th number in the bth row of Pascal's triangle. So if B is 3, then I can ask for 4 numbers. A0, A1, A2, and A3. And K will send back 1, 3, 3, 1. And Pascal's triangle has a special quality that if you add all the numbers in one row, you get the power of 2 for that row number. So 1 plus 3 is 4, plus 3 is 7, plus another one is 8. And the next row is 1, 4, 6, 4, 1. 1 plus 4 is 5, plus 6 is 11, plus 5 is 6. No, it's 4. Plus 4 is 15, and the 1 at the end gives me 16. It's max power of 2. Ugly doggly. Not going to waste time. Beautiful stuff. Fibonacci. This is so much fun. There are a million questions I can ask about Fibonacci. Even though it's the same thing, this has got amazing opportunities for questions and tests and practical tests. So this is so straightforward. I'm not going to write it. It's almost exactly like the previous one. But it's still interesting to see that Fibonacci sequence. In fact, you can think that there are millions of sequences. I can do anything with the last 2 numbers, or last 3 numbers. I don't even have to add them. I can say, what happens if I have the previous number and the one before that minus the one that's 2 back. So it'll go 0, 1, 1. And this next number will be 1 plus 1 minus 0. That'll still be a 2. And the next number will be 2 plus 1 minus 1 is still a 2. And the next one will be 2 plus 2 minus 1. That's a 3. It's going to carry on like that. And the next one will be 3 plus 2 is 5, minus 2 is also a 3. No, so the 0 is 1, 1, 2, 2, 3, 3, and then perhaps 4, 4, who knows. All sequences of this kind that have some kind of operations on the last n numbers, it's called Lucas sequences. So it's a little more general than Fibonacci. Okay. Now, this is something I wanted to say in class on Wednesday, but I didn't get to it. So it's a good thing that I put it in the chat because I really want to talk about it. It's in the textbook. It's an important part of recursion. If we do Fibonacci, so here is Fibonacci. Here is the system, and at least on my computer, I can run it up to 64. Sorry, 46. Dyslexia this morning. Okay. And after that, it starts taking longer and longer and too long, more than 5 seconds at least. Oh, here we go. 46 takes. I think it only takes 6 seconds, but it's longer than I'm prepared to wait. And if you go up to 49, takes about 2 minutes. And after that, it takes something like 10 minutes, and then it starts taking hours. Just half an hour, hours. So Fibonacci very quickly becomes takes very long to compute. And there's a reason for this. I mean, we are computing, to compute the Fibonacci number for n, I have to compute the Fibonacci number for n minus 1 and n minus 2. So for small numbers, it makes a difference, of course, but for big numbers, n minus 1 and n minus 2 start quite close together. So you can think of this as asking the computer to do this work and this work, which is almost the same. So each time I compute Fibonacci of n, I do 2 pieces of work for n minus 1. I do the work for n minus 1 roughly twice. Of course, this is a little more than this because this is n minus 2, but let's say that the cost of these two are about the same. So if I start out with a cost of 1, to compute Fibonacci 2, I'll do 2 pieces of 1's work, so that'll give me a 2. And for Fibonacci 3, I'll do 2 pieces of 2's work, that'll give me a 4. And each time the work doubles. So the next one will cost me 8, and the next one will cost me 16, and then 32, and then 64, and 128, and so on. So the work for Fibonacci is exponential, which is why the time doesn't exactly double, because the computer can make a few little savings in a few places. But after a while, once it gets to big numbers, you'll see that it really doubles. It grows exponentially. So how are we going to ever compute the Fibonacci number for 100? Well, firstly, it'll probably be a very big number. I won't be able to fit it in a log, or perhaps I will. Will I? Won't I wonder. But if I want to compute it, I'll have to make Fibonacci a lot faster. And there is this technique that explains that's called memoization. I know it looks like memorization, spelled wrong. What is it? Well, it's the name of the question, so let's go up here. I know memorization looks like I tried to spell memorization, but I forgot how. But that's not how it works. I'm kind of memorizing things, but this is really something else. It's called memoization. And what it means is that you remember the results, you memorize the results for previous times that you call the function. So every time I call Fibonacci for a certain n, I'm going to store that result. It's illustrated down here, so let's look at it. All this code here in main, that funny code that you may not like, it's just to record the time. It's useful to know, but it's not critical. So how does memorization work? Firstly, I need a place to store all these function calls, all these results. So I declare an array. Step 1 is to declare an array, and I call it store, but you can really call it anything you want. If I'm going to compute 100 results, so if I'm going to call Fibonacci for numbers up to 100, I will need 100 places, 100 slots in the store array to store my 100 results. If I'm going to call Fibonacci for up to 1,000, I'll need 1,000 slots in my store array. So the size of the store array determines for which values I can call Fibonacci. Now, our approach to memorization is pretty simple. You can make it more sophisticated, where the size of the store array doesn't limit you. So even though the store array is only 1,000 slots long, you can call Fibonacci for numbers up to 1 million or any number. But in our case, it's pretty simple. So we're going to stick to the simple solution. I have a store array. It's large enough to store all the values I want to compute. Then, this store array represents my memory. And initially, I know nothing. I know what the values of Fibonacci are, but it could have been some other function. So I'm going to pretend I know nothing, and I have to somehow indicate that it's stored. So I'm going to put a value in each of the slots of store to tell me that this value is unknown. And in the case of Fibonacci, I pick -1. If I were working with a function that actually sometimes gives -1 as a real result, I'd probably put something else in there. And once again, if you're more sophisticated, you don't need to use -1 or or some other special value. There are other ways of doing this. We're going to keep it simple. So a full store of -1, meaning I know nothing. And then I've got my original function. I said it's called G because I wanted to emphasize that it's not limited to Fibonacci. But I have some function G that I want to memorize because G is taking too long. So what I do is I make a new function. What I do is I change the name of G to old G, just there in the heading. Okay. So in this case, I want to memorize Fibonacci. I change the name of F to old F, but only there in that one spot. In the body of F, where it calls itself recursively, it's still called big F. So only there in the declaration do I change the name to old F. Just at the top, and it still calls big F down here, which now presents a problem because I don't have a big F. But the last step, step 4 of memorization, is to make a new function called G, or F in our case, and it always has exactly the same form. This new function will always look like this. It doesn't really matter what the function is called that I want to memorize. It always looks like this. It first checks, do I not have a value for the n that I want to compute? Is n unknown? If n is unknown, call old G, old F, with n, and put its return value in my memory. And then I send back my store in, the value I remember. So if I've already calculated Fibonacci for, let's say, 5, then store 5 will not be -1, it will be the 5th value of the Fibonacci sequence. 0, 1, 1, 2, 3. Store 5 will contain 3. This if won't execute, and I'll just send back the 3. But if, let's say I've never called Fibonacci for n equals to 6. The 6 value in the Fibonacci sequence is 5, but I've never calculated it. So store 5, store 6 contains -1, which means I haven't calculated it before. I calculated using my function, which is now called old G, old F, and I put the return value in that slot, store 6, and then I send back store 6, which will now contain 5. G, old F, well, it's now confusing because I'm talking about old G and old F, and G and F, but let's switch to old F. So I changed just the name of my function, keeping the recursive invocations the same. Then I made a new function F, which contains this little shell code, which checks the memory first. If it can't find it in the memory, then it calls old F to calculate the value. So how does it work? I want to calculate the value for old F for, let's say, n equals 6. I don't have it in my store. I call old F. It starts up. It calculates Fibonacci, but it calls big F. So it'll call this routine again to see perhaps another value for n -1 or n -2. So this function calls that function, and this function calls this function again. It's a kind of recursion. This calls that, that calls this. It's a kind of recursion with 2 different functions calling each other. Instead of just having the normal recursion, we have one function calling itself. I now have 2 functions calling each other. In fact, it's called co-recursion. And I can extend this. I can have 3 functions where function A calls function B, and function B calls function C, and function C calls back to function A. So I can have a loop of 3. For sometimes, that's what I want, or what I need. Okay. What does this help? If I want to find the value for Fibonacci 100, it's going to go all the way down. And for all the values below 100, let's say 50, That Fibonacci of 50 will probably will need to be calculated many, many times. But with this memorization, I'm only going to calculate it once. I'm only going to calculate the value of Fibonacci for n equals 50 once. And I'm going to store it and remember it. And I'm never going to do that work again. So when I need, yes, full stop. Okay, so down here is main. It says, okay, let's go up a little bit. Here is my store array, and it's a global variable inside this class. And then I've got my old f function and my new f function, and I've got my main function, which says, let's allocate the array. Let's ask Java for space to store the array. Fill the store with -1s because that's my sign, my one token, there's a special name for it. That's the terminal. I'll think of it as Zen. That's a value that indicates that I don't know a certain answer. Fill that whole store with -1s. And then I do exactly what I did before. So this code hasn't changed at all. It's exactly the same as the code above. All I did was insert a few lines at the start of main. So to memorize Fibonacci, I had to change the name of the function, add this little extra function, add an array, and add these lines to the top of my main function. And now hopefully Fibonacci will go much, much quicker. How long does the f function take now? I don't know. How long does it take? Does it say in the solution? Oh! No. No, it doesn't say. I remember now. Oh, here's the solution. Okay. Fibonacci. Oh, never mind. But I do happen to know, at least on my computer, in the labs will be different. But when I executed the memorized Fibonacci for all those 46 numbers, it executed in 0 milliseconds. Which doesn't mean it was instantaneous, it just means that it was too fast for the computer to even measure how many milliseconds it had. So we speeded this up tremendously. Truth be told, I haven't checked how long it takes to go up to 100, which is stupid because it's really interesting. So I'm going to check it now, if I can. Let's just see, do I have... do I have Fibonacci? No, it's not on this computer. Oh, that's so stupid. Oh, never mind. Let's just write it. Memorized Fibonacci.java. Should do this in Eclipse, but I'm just much quicker for me to do it here. Copy all these lines down there. Now I've got these ugly line numbers, but I can delete them. Java C. Okay, Java. Okay, so up to 40 seconds on this little computer, it now takes 0 milliseconds, up to n equals 45. But what I'm really interested in is Fibonacci 100. So let's change that. Let's change it to print all the values up to 100. I know there will be a mistake, so let's see. So somewhere here, in fact, just after 46, these numbers simply became too large to fit in a long value. After 46, actually int, because I was using int in this program. Let's just change that. Let's change it. Oh, there are so many ints. Long, 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 long. No, not that. Stop the. Okay. This parameter shouldn't be. Let's be sensible. Alt F should take an int parameter, but it returns a long value because the parameter is up to 100, but the value of the Fibonacci number may be much larger. And the same for the new function f. And then here, this I should just be a normal variable, and k can just be a normal variable. That's fine. So again? There we go. Okay, so this time I got up to 92 before these numbers, the Fibonacci numbers, became just too large to store in the log. So to go beyond this point, I need to do something special, which we're not going to cover in this course. But despite the fact that these numbers are wrong, these time measurements are accurate. So even if I fix my program so I can go beyond F92, the times will still be the same. As you can see, it's blindingly fast. In fact, it will keep on being very, very fast up to, I don't know, perhaps 1 million. That Fibonacci number will be extremely long. Up to 1 million, it won't take any time to calculate the Fibonacci number. That wasn't exactly what the TUT was asking. It wanted you to do this memorization. It wanted you to do that Fibonacci, the assignment from the previous exercise. But let's close it, as long as you understand. Good. And this last one is this funny function in computer science called Ackermann's function. We use it a lot, but it's a little too sophisticated for our course. But we can at least talk about it a little bit. So I've got these functions. I've got one function, s, that takes a parameter and simply returns n plus 1. And it's called s because it's actually short for successor. It calculates the successor of a number. So I give it a number n, and it calculates the successor of n. And then I wanted to mystify you with these recursive functions. Unfortunately, A is a bit of a disappointment because A actually stands for what it does. A calculates the sum of I plus j. So A can stand for addition, but I was too lazy to think of other letters to avoid that. I'm pretty sure I could have fooled you. Okay. So A is defined in terms of s, so it uses the successor function, and it also uses itself, it calls itself recursion. But it doesn't do anything else, it doesn't add numbers. It subtracts 1 from j, but that's only allows you 1. Come on. It doesn't add, it doesn't have a plus sign in it, but still it calculates addition. And it also doesn't use any constant, except for the 1. And it uses the 0 as well. But A implements addition of two numbers I and j. So I don't really need addition, we don't need addition in mathematics. Just successor is enough in mathematics to define what it means to add two numbers. B is fortunately not clear at all. B doesn't stand for anything, it's just the next letter. But this B function calculates multiplication. So A of I and j is the same as I plus j. B of I plus j. Damn it, do I say this later on? No. B of I plus j is the same as I times j. And once again, B is defined in terms of A. So just like A uses S, B uses A. And it has to add that parameter I. and then it calls itself recursively. And it doesn't have a multiplication sign. It doesn't even have an addition sign in the function. C, what comes after multiplication? No. Let's say that you're once again in the final, not the final exam, one of those aptitude tests where you have to say an apple is to an orange as a donkey is to a dolphin. That's right. So multiplication is to addition. Sorry, no. Addition is to multiplication as multiplication is to exponentiation. So C calculates exponentiation. It's the power of, it's I to the power j. Once again, it's defined in terms of B, and just like B was defined in terms of A, just like A was defined in terms of S, and it's defined in terms of itself, C. And lastly, what comes after exponentiation? So addition is 2 plus 2, 3, let's say. Multiplication is 2 times 3. Exponentiation is 2 to the power of 3. And super exponentiation is? Any guesses? So the super exponent of 2 and 3 is 2 to the 3 to the 2. I'm repeating the exponentiation 3 times. Okay, it's 2 to the 2 to the 2, yeah, just 3 2's. And 2 with the super exponent 5 is 2 to the power of 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 2. So I've got 5 2's stacked up below each other. So the idea was that you probably couldn't get very far past 4 for K, if you got this far. Okay, I'm going to stop now. On Monday, I'll bring along the tests, the first tests. I'll hand them out in class, you can look at them, and then you have to give them back to me at the end of class, because otherwise I'm not going to put your marks in the system. I have to have those tests. But I'll work through the first test. On Wednesday, I'll work through the last test, the written test, and on Friday, you'll write the third written test. Okay?